All right, so in the beginning, I was thinking to prepare a Flink-related talk, but after listening to all these nice talks on different systems and techniques, I decided to do something more broad and put all, let's say, streaming systems together under the same umbrella. Okay, so actually, I didn't expect it, but it was a really good experience so far. I've learned many new things. Yeah, I thought I would just listen. I would just hear the same and the same, but it's actually many new things that came up on this school. I met very interesting people. I think we have some of the biggest minds in the databases and the service systems here. And that's very exciting. And it's not just that. I mean, we are in a very beautiful place, actually, right? It's amazing. There's a lake nearby and so many trees, and it's really beautiful, I would say. And in situations like this, I start wondering sometimes. I mean, like every paranoid person, what can go wrong, right? As we know, we have many secret smokers here among us. Maybe I'm one of them, but I don't say it. And smokers go outside like in random times, and they go far away so people don't see them, and they smoke near the forest. And okay, so can something go wrong? I mean, so maybe. I mean, it's paranoia we're talking about here, right? So it might be a huge fire spreading right now. So how could we avoid this, actually? I mean, we have so many big minds here, so many data analysts, future innovators, people who come up with solutions, right? I don't know. Do you have any ideas how we could? I mean, ourselves we could solve this problem. How could we prevent fire? Don't. Okay. Yeah. I know. But let's try something else. I mean, maybe preventing fire is the same with detecting fire, right? I mean, if we detect a fire fast, we can just go there and call the fireman. So detecting is more like a data analysis problem, right? We detect something in data. So first we need to actually generate data, right? So let's start analyzing this problem. So what we actually need to do is to generate data. So we could actually play some. We could buy some cheap Arduino chips and put them around the building and maybe in the park and next to the lake. And then we could connect them to our MySQL database that's in the basement of this building, and then start writing the current measures, the current events on this database. And what we could actually do is then to just write some ad hoc queries, send them to the database, and see if something's wrong. Maybe do some complex time series analysis, just to find out whether there's a fire, there's some specific pattern, right? What could a pattern about fire be?
Should be an outlier, actually.
Outlier.
It's not that often that occurs.
True. Let's say we have temperature and smoke events. I mean, these are the most basic sensors we could use. Perhaps smoke and high temperature happening together in some way, right? One after the other. That could be a good indicator, maybe, right? So let's say, yeah, our queries detecting high temperature and smoke in any order, happening close together. But I'm still paranoid. Okay, this sounds good, but we need to just sketch it and see if something can go wrong, right? So this is a global timeline. Our sensors, our database, and us. And let's say there's a fire happening somewhere there, and here's a smoke coming up and high temperature, and these events are being propagated to the database. So we just write smoke and temperature events in the database periodically, right? So the sensors generate this data and they just write it. So what we do there is to, whenever we want, we just send a query. It takes some time to actually, look through all this time series data and detect these patterns. Probably, if there's a fire detected, we get it back and we call the fireman. So we send the first query. There's nothing detected because maybe we just read the smoke events at that point. And we go to bed, we do something else, and then after a while we just check again, just to be sure. We send a query to the database and see if something's wrong. Well, the thing is, we actually lose all this history here, right? So there might be a fire spreading, and our query didn't actually make it. The first query didn't actually make it to detect this pattern. And the second query might be too late, actually. So we're talking about real time. It's real life here. I mean, real time. We need to find something fast so we don't die. Because everything might get burned, actually, at some point, right? Us as well. So we need to come up with something better. And I think it's becoming more and more obvious at this point, right? We need something like a standing query. We need a query that we can actually deploy and let it consume events by itself. Never end, just keep running and consuming events and trying to find patterns incrementally, like event by event. Okay. So whenever that happens, let's say the fire spreads, the query will identify it, we will get a push notification, and we'll call the fireman. So we can also automate this process. So we can actually go to bed and wake up in the morning safe. I mean, this is sounds like a safe solution, right? So let's see what these standing queries are. I think these are really interesting. So what is a standing query? This is actually another name for data streaming. I mean, streaming jobs, streaming topologies. It's the same thing with a different name today. So we're talking about the data streaming paradigm. So this is just the preliminary, what our assumptions are about when writing these queries, right? So first, our data is unbound. That means that we're consuming events endlessly. There's no end. And also our queries are also being evaluated continuously. They don't just sleep for a while and then getting redeployed or something like this. The queries are active, right? And queries can operate either on the full data or maybe in specific chunks in data that we are interested. These chunks can be called windows. And here are some basics. So we have events. Events are the smallest elements of computation. They're like the sensor update, let's say in our case. And they usually respect a schema. We know what to read from these events. Let's say they have a timestamp, they have an area indicator, and they also have a metric. And these events compose data streams. A data stream is a sequence of events of the same type or from the same source or something like this. They have some semantic meaning, right? And stream operators are basically standing queries that actually consume different streams and generate new streams. So they actually take events from input events and generate output events continuously. What is very important is that we cannot reprocess an event. We just process an event and we throw it away. So everything is consumed once. There's no backtracking here. There's no indexing. We need to be very careful to actually make use of every single event we process at the time we process it. And if we put many operators together, we can actually create something like a topology, something like this, a very complex network of operators that actually do something useful here. And we usually call the input operator sources because they fetch data from the outside world. And we also call the ending operator sinks because they actually write something to the external world or indicate. All right. So if I could just go through all the stream processing, let's say literature and all stream processing systems and select the most basic, the common denominator of all the systems, then I would pick 3 abstractions that you need to have in mind when creating streaming algorithms or streaming queries of any kind. The first is windowing. The second is synopsis, more correctly, which is the state of our operators. And the third is partitioning. So let's see each one of these. So first, windows. Why do we need windows? There was this question before a few times, right? Why do you think we need windows? Why don't we just process everything infinitely, and why do we need to create chunks?
Older data might lose relevance over time.
Exactly. I mean, that's very important, right? We're mostly interested in something that happens in the near, in the near present. Yeah. We're interested in fresh data, let's say, right? We need to detect fire from data that we receive now, not through the whole lifetime of this building, right? Well, there are more reasons. Actually, there are certain operators that work over Windows. There are blocking operators like specific joins, for example. Professor Volker mentioned it before in Cosmin. So there are certain types of computation that we cannot just run purely incrementally, right? We need to put some bounds there. All right. So Windows can be composed, in most of the times, Windows are composed out of 2 single, let's say, policies. Or they have 2 parameters. One of them is a range. So that defines the length of the window. So which elements we will put in our window when we invoke a query. The other parameter is the slide, which is basically the frequency we run our computation. So how often do we want to run the query? How often do we want to check for fire, right? And we can say that we can just unwrap our operator with a window, and that puts some bounds there on the data it actually processes. So everything, this F operator process would be within 1 minute, and it will run every 20 seconds in this case. And Windows can be sliding. I mean, if the range is higher than the slide, then it's a sliding window, because we have overlaps. If the range is equal to the slide, then we have tumbling windows. So we process everything once, basically. And we also have jumping windows. So we could actually also lose data. We might be interested only to run something periodically and only consider a small amount of data. That's fine, right? So these are the most common window types.
What about approximate windows when you're sampling?
So I think that's more into the second part, which is synopsis. So unless we run something very simple like a filter, let's say, or we just do some simple transformation of the data, we always need state. State is very important. So when we process something continuously, we need to keep a state that reflects the whole history of the stream we process up to this point. In the case of window, the state is basically reflects the data that's within the window, right? But if we run a query continuously, then a synopsis. I really like this word. It's not because it's Greek, but it's because the meaning is very correct. It explains everything. So in Greek, it means summarization. It summarizes everything we process so far. And it's in principle an operator state, right? Some good examples are samples. So a sample is a synopsis of a stream we processed so far. It could be a histogram of the data. It could be a sketch, which is a type of approximate data structure. You actually heard about some sketches this week from Jeff Altman. And we will talk about them as well. Even a state machine actually is a synopsis, right? A state machine reflects the current state. The current state is a function of the whole history process so far. So that's a synopsis. I don't know if you like this generalization, but I think it summarizes pretty much everything. And it's also very important because the state defines the future generated events, right? So in the lifetime of the usual steps an operator takes is to first take the current state and an input tuple, and then update its state and generate a new tuple based on the state. So it's something that actually affects the future, the generated streams. So okay, these are very easy questions, but just for a recap. So let's say our operator is a max. What is a synopsis? It's basically one number, right? The max. If we're talking about an arithmetic mean, then the synopsis is what? Yeah, exactly. It's a sum and a count. That's our synopsis. That's all we need. It's the minimum amount of data, of state we need. The standard deviation is similar as well. Like the arithmetic mean, we also need the square of the sigma, right?
Exactly.
Yeah. So rolling aggregations are easy, and the synopsis, if you notice here, the synopsis is not approximate. I mean, it's we get exactly the result we would get if we would run this in a batch mode, let's say. But if we go to approximations, things get a bit trickier, right? What if our function is to generate a uniform random sample of k records over the whole stream? What would the synopsis be in that case? I mean, that's easy as well. If you think about it, we want a sample of k records, so our synopsis is k records. We can update these k records with a reservoir sample or algorithm or something like this. There are many strategies, right? But that's our state, it's k records. But that's a bit trickier, actually. And for the second one, you need to remember Jeff Allman's lecture, I guess. So we want to filter out, we want an operator that filters out distinct records over windows of 1,000 records with up to 5% error. So we know an error, we know how many records we want to create a distinct filter. What's our approximate data structure?
That's a good question. So what is everybody should know.
Yeah, you were here, I saw you. You could create a hash map, but that's not an approximate data structure. I mean, the hash map would increase infinitely, right? So the more you process, the more elements you would put in this hash map. But we can also afford more, because the hash map would have 0% error. Here we can have up to 5% error. So we need an approximate data structure. Bloom filter, yes. And how do you define the length of a Bloom filter? You need two parameters, right? So you need to know the false positive error and the number of records you could possibly put in. So that's our synopsis. It's a Bloom filter in this case. All right. I could talk about this forever. I mean, there are very cool synopses around, like sparsifiers or spanners. We actually use them for graph streaming projects. These are approximate data structures that let you run continuous approximations on edge streams and basically detect things like sorted paths, approximate sorted paths. There are also chain detectors. They're very, very interesting for stream processing because you can find out whether the distribution of your stream changes. And things related to machine learning, models related to machine learning, like incremental decision trees. This is a tree model, and it basically builds over incoming streams. And it also classifies other incoming streams. There's a Hoivning tree implementation that's very popular. One of the previous EIT students actually worked on this last year, and we had really good results. All right, so let's go to enough rambling. Let's go to the third thing, partitioning. So partitioning is also very important. We need to partition our data because our input might get too large. We cannot possibly process our input with the throughput. It actually comes with an injection rate. We need higher ingestion rate, right? So we need to increase the parallelism of our operators. We need to put more instances there to handle the incoming streams. And the question that arises is, how do we partition our streams? I mean, how do we allocate input events to consumer operators? There are many standard partitioning techniques. You can think of a partitioner like an operator that actually takes events and selects the right consumer to forward these events. Anis knows more about this. If you talk to him, I think he's working on this topic. But let's say the most typical partitioners are the broadcast partitioning. This is when we actually forward all data to all operators. It sounds stupid, I know, but it's not stupid actually. Let's say you have a training model. You want to build a training model, and you want to classify user events. So the users are actually they want to listen to music in Spotify, and at the point they actually click radio, the system needs to recommend the song. Let's say you have like 10 million users, right? At the same time they click. You need to handle all this throughput, right? All these events. So you need to pass the user request through the recommendation system and offer an answer. Well, if we do broadcast partition, we can actually replicate a machine learning model that's identical and forward all these user events to each model. And yeah, recommend songs. For techniques like collaborative filtering, this works pretty well. Otherwise, it's better to partition your data by user, right? Then we can also shuffle our data. That's the best way of doing load balancing, right? Because we actually, all operators will receive the same amount of data, basically. And remember that the state is also a function of the input. So that means that also the state will be load balanced as well. Then we can also do things like partition by some key, right? Let's say we partition these balls by color. So all balls of the same color will be forwarded to the same operator. All right. So that's enough. Actually, we know everything we need to actually design streaming algorithms. Here we have sensors. Let's say they generate. So first we have the temperature sensor. It generates events of temperature updates where we actually append the area as well. And we also have smoke events. So whenever a smoke is detected in an area, there's a generated event forward to our system. And our system, everything our system needs to do is to actually create a stream of alerts. So we just need to output an alert whenever a fire pattern gets detected. So let's go into these three, let's say four, because we need to define operators as well, concepts, and see how we design our pipeline or our standing query. So first we need sources. These are the easiest operators. They just need to fetch these events and disseminate them through through our operator graph. Then we might need to do. Okay, here I really want to put an aggregation, but I didn't find good reason. Actually, I found just now. So we might want to do an average of the temperature. We might not want to detect patterns over individual events, and that's the same thing because many sensors have spikes, have faults, and they might generate faulty data. Like they might generate a very weird temperature at some point. I mean, you don't know, right? You can't trust it. If you have many of these sensors and you in the same area, you can just pick up the average, or the average of the average temperature, per area, let's say. And our final operator basically takes these averages, takes the smoke events, and runs some pattern recognition and outputs alarms, right? All right. I think that's pretty cool. So we have all operators we need. What about partitioning? So we have area, right? So there's an area. Area is dependent on every event. So what we can actually do is to identify fire within every specific area. I mean, that's reasonable, right? It's actually useless to correlate events from different areas. I mean, there might be a fire on the other side of the building or near the lake. So we want to do location-based pattern recognition here. So let's partition all events by area. That means that we will run, every operator will just take all events of its specific area. And what about windowing? So one thing we could do here is also to, since we want to process fresh data, is to window our average, basically. So we want the sliding average of 20 seconds every 1 minute, for example. So we will fetch a rolling average and detect fire with a 20-second granularity. That's not bad, actually. So let's go to the fire alarm. So we need to take average events over a window and smoke events at the same time. And we want to detect patterns. How do we detect patterns? How do we detect patterns? I mean, do you know any technique?
We might go to a different state when we see the first part of the pattern.
State, right. So we need a state machine, basically, right? And we need to see the transitions we actually need to follow to detect that pattern. That's a very it's a very common way of doing pattern recognition, to write a state machine. And that's also cool because we don't need to keep much state, basically, right? We need to keep one state. So basically, if we say that a high average temperature is more than 4 degrees and a normal temperature is below 4 degrees, so then what we actually need to identify, let's say the bad temperature is the red one, we need to identify sequences of high temperature and smoke, or smoke and high temperature, right? I mean, those two patterns in our event stream. How many states do we need for that? So we have the, let's say, OK state, right? We start from that. We also have the alert state, the fire state. And we need to detect 2 patterns. I guess we need 2, right? So we can go like this. We have an OK state. If we receive a high temperature, we go to a hot state. If we receive a normal temperature, we go back to the OK state. Remember that it's an average temperature, so there are no faults here. Right, and if we detect first a smoke temperature, then we need to wait for a high temperature and go to a fire state. All right, so we have everything we need. We have our pattern recognition algorithm here. Our synapse is 1 state. It's the minimum we can keep. 1 number, let's say. So we put everything together. It looks like this, right? So we need to design a topology that looks that has all these operators put together. It looks actually reasonable, right? All right. So let's now select a system to actually run this query. There are actually many systems around. You see that we have proprietary systems. We have open source systems. There's a lot to choose from, right? I mean, you heard yesterday about Google Dataflow. It does streaming as well. IBM Infosphere, it does streaming as well. Microsoft Azure is has a quite new streaming, let's say streaming API. But we also have these awesome open source projects like Flink, Samza, Spark, and Storm. And actually, how did we get to having all these systems? I mean, the thing is that there's a very long evolution of ideas and systems, concepts and systems that actually led to where we are today, actually. And many of the old ones were quite unique, actually, and they used to have features that we don't have today. But what we actually benefit today from is high parallelism and distributed processing of events. Maybe you know some of these systems you see here. Probably you know the most recent ones, like Storm, Flink, Millwheel. Millwheel is like the precursor of the system Google was using that led to Dataflow. All right. So this is very important here. So there's no black and white, basically. There is no system that does everything and a system that does nothing. I mean, all of these systems do something, and they do it differently. So if if I couldn't categorize this system, so I just put them in this axis. This axis basically shows goes from purely compositional to declarative. Compositional, I mean systems that give you a programming model that is very basic. So you get a very low level hooks to implement your query, while declarative actually lets you explain just what you want to do. So it's like how to what scale, right? So I think Dataflow and Flink are very close together. They offer a good trade-off between how and what. Yeah, we will see in more detail. So basically, systems that tell you, that give you hooks on writing how you want to do something, like Storm and Samza, basically give you access to a programming model that is very close, tightly coupled to the actual execution of a streaming algorithm. So,
how would you relate a SQL streaming to that? And SQL also has a streaming.
I would say it's up there, right? So that's why I put Azure on the very declarative side. So Azure offers a SQL highly declarative API for writing queries. So the more we go up, the more the higher abstractions we actually create our query from. And we can also say that the higher you get, the more closer you are to a data analyst. The lower you get, the more to an engineer. So depending on your skills, you might select a system that actually fits your needs and your knowledge, right? Okay, so this is the execution graph. Storm and SAS actually give you access to low-level operators. So you actually need to implement the whole logic yourself. You need to implement what each of these balls here does. And while Spark, Flink, and Azure actually give you access to, sorry, Millwheel, give you access to very abstract data types, like data streams, these streams, you remember from Pacostock, and parallel collections from Google Dataflow. And you can actually run very high level, you can really easily explain what you want to do by applying transformations on these data structures. I'll go very, very fast here. So Apache Storm basically is I'm just explaining Apache Storm because it's a very low-level system. It's like one of the left end of the scale. And basically, you need to implement the whole logic of each operator. So the operators are called bolts. They do arbitrary data manipulation. And the sources are called spouts. And they just listen to data events and generate streams. This is how you this is how you write your topology on Storm. So you need to actually implement all these operators, bolts. I don't show here because it's a lot of boilerplate code to write a bolt. But you define your whole computation like this. You need to put all things together and create the physical topology of your query. Actually, one thing I didn't mention here is that the more you go to the right, the more optimization benefits you get. So the higher you get, the more you give to the system. The higher the API, the more access you give to the system to actually apply optimizations, right? And this is very cool because in the case of Flink, for example, we submit. You see here, we just write a job in a very declarative way with functional programming. We define windows and streams like this. We group by, sum, and so on. And we send this simple instructions to the Flink client that actually apply some optimizations, like operator fusion. You saw fusion from Cosmin's talk. We actually do the same thing on Flink. And window pre-aggregates and different strategies that the user doesn't need to bother, right? And then it ships the actual physical, the logical topology to the runtime. The runtime creates a physical execution of this topology. And that's pretty cool, actually. When we go to the execution part, so here we saw the programming models, but what actually happens here is fundamentally different in the different systems. So here we have two paradigms of execution. The first paradigm is real streaming. It's a, distributed data flow model where you schedule operators once, you put them in the cluster, and you let them consume data and update their internal state, basically, and disseminate data to other operators. Which actually maps to the logic and the whole concept of streaming, right? Pretty well. In the second case, we have batch execution. We can also call the first one pipeline execution. There are many names, but you get the point, right? The second one is the batch execution, is where we actually try to simulate streaming over batch processing. And you know how batch processing works. You need to schedule your computation in a cluster, right? And it's very easy to do things like fault tolerance and apply large-scale transformations on your data. But when it comes to streaming, you need to do things like batching events. So in the case of Spark, for example, we have only time-based ingestion. So you can think that on Spark, every computation is a time window computation. So we start with a time window, and we create other time-based windows, and we process those windows throughout the way. And whenever we create a new batch, we actually schedule a new batch job, which doesn't sound really great for streaming, but it has other benefits, like parallel recovery, for example. So it's not really completely bad, right? But you actually lose in other things, as we'll see. So let's say Windows. So let's go through our three basic things. We have Windows, synopsis, state, and partitioning. So when you have Windows, in the case of Spark, for example, we only have access to time-based windows. So, and this gets awkward sometimes because we need to define the windows that are derivatives of the initial granularity we actually ingest our data. So it's kind of restrictive in this manner. Fling, on the other hand, has a very expressive way of defining windows. And this is something I like bragging about. I mean, we can define two things, range and slide, right? So range can be, so windows are policy-based. And we have two policies here. A policy that defines the range and a policy that defines the slide. All of these policies can be of any metric we want. So it can be time-based or count-based. So we can have a window that keeps a fixed state of 100 tuples. We can actually bound our state, basically and subsequently our like data, the size of the buffer we want to keep in memory. And we actually control also the frequency based on time, for example. So we can actually say to the system, compute this thing every 10 seconds with keeping a state of 100 tuples. That's very powerful, actually. And you get this benefit because you have a real streaming model. You can actually control each individual element in the system. Windows on Storm, you see how custom it is? I mean, the user needs to write all these custom things to explain Windows. There's no Windows support, basically. And that's because it's a very low-level system that doesn't give any abstractions to the user.
Assembly language.
Yeah, it's almost assembly language of streaming. Exactly. When it comes to partitioning, I would say Fling and Storm are quite powerful. They give you full control on how you want to partition your stream. I mean, you can actually do things like shuffle your data, you can forward, and in any case, you can do custom partitioning in both of the systems. You can actually write your own partitioner based on a Bloom filter, for example. So you have full control of how you want to disseminate your data. When it comes to Spark, actually, since we don't have a real streaming system, on Spark we actually have access to only a couple of ways to do key-based aggregations, for example, or repartition the data into more workers or less workers. But that's all. I mean, it's not a streaming system, so we cannot really control the dissemination of the data, right? We're talking about batches anyway. So synopsis, well, so how do we define states? That's a big issue in most of the systems. On Storm, so here you will notice two things. Let's say we want to compute a maximum, right? So on Storm, let's say we do group-based partitioning. So we do key-based partitioning. That means that every key will be forwarded to one operator. So this is what our max operator would have to do. This is also the hash map disease. You need to keep a hash map of all mappings from keys to aggregations, or from keys to state, basically. So you need to do this thing manually here in Storm. And OK, apply your logic based on this.
So you're doing max per key?
Yeah, it's a max per key, exactly. So in this case, you need to keep the max per key manually. And the state is anything arbitrary you define there. Of course, that doesn't give any hook to the system to actually do state fault tolerance. So that means that when this operator goes down, this state will get lost. I mean, the system isn't even aware of this state. In the case of Flink, we have two things, maybe three, I don't know. So first of all, we partition by key, easily as that. We do key by key. And then whatever aggregation we run after that actually runs per key. So we don't need to keep all keys in our user-defined function. We just define one state, basically. And that state is mapped to a key, to the key that we actually process at the time we actually run this. And it's actually a new feature. It's not, it doesn't exist in previous version. So we actually have all operators, replicas of all our operators, transformations with state. So we can actually define a flat map, for example, with state to do our max, to implement our max. And in this case, what we have to do is first to define our state. Our state, as we said before, of a max is one number. So whenever we have an input of higher than our current max, we actually need to replace our state with here. So we need to replace our state with the current max and disseminate the max. We need to return a list because it's a flat map. Otherwise, we just return an empty list. We don't have a new max, and we just keep our current state. In case we have no state, this is the initial state. The first tuple.
Is a pair, right?
Yeah.
One is what is the flat map does normally, and what is the next state?
Output and a new state,
Exactly.
basically.
That's just to make it.
Yeah. Yeah, maybe I'm going too fast. I don't know. I just want to get through. How much time do I have? Oh, OK. That's enough. How about state in Spark? So as I mentioned before, we don't have state. We don't have long-running operators, right? It's not a system where you actually schedule the operation runs forever. So we need to simulate state somehow. So state can be basically, the only way you can define state on Spark is to, for streams, is to actually map state to your output of an operator. So the output of your operator is the new state. The RDD contains the state of the next. So there is an operator that actually makes this automatically for you, the update state by key. It only works by key. You can have a global state. But you can use broadcast variables, so that makes up for it. So yeah, I mean, you can do things on Spark as well. It's not like you can do stateful combinations on Spark. It just gets a bit awkward when it comes to streaming. So let's go back to Flink and to our fire alarm case. And let's put everything together. We learn how to do windowing on Flink, how to define states, and how to do partitioning. So we get temperatures. Let's say in our first implementation, we fetch the streams via TCP sockets. So the sensors actually connect to our Flink cluster, and they just start like flashing events there. And then we actually partition those. You see key by. We partition those events by, is there a laser?
Yeah.
Ah, yeah. We actually partition those streams by area. OK, so we get temperatures and smokes. Then we need the average temperature in a sliding window. So we define an average operator. I won't implement the average operator here because Gyula will show more about the practical part of Flink, how to write awesome pipelines. So I do windowing of the temperatures. So we have a sliding window of 5 seconds, of 60 seconds every 5 seconds. We create the average temperature per window with a map window operator. Then we flatten it, so we have a data stream back again. And we repartition by area, because then we need to reconsume this and create our fire alarm. So we have a binary operation here. We have a binary flat map, because we have two types of streams. We have average temperature and smokes. So we connect the average temperature with the smoke stream as it is. We don't need to change anything. We just partition it. And then we do a key-based flat map on those two streams. And we print the results, basically. We just print an alarm. We might have a parser there on the client side. All right. So yeah, I mean, we made it, right? That's it.
I mean, that is the whole application.
So can we just let this run and go to bed? Do you think it's enough? I mean, we wrote the query, we just run it, we connect the sensors, we're done, right? We're safe. Or? Well, okay, let's say we go to bed, but the sensors start burning. I mean, they get faults. So if the sensors break, then we're doomed, right? The sensors generate the data. We don't process any data. We don't detect fires, so we get burned. So we need to do something about this. Okay, I have an idea. We can just add more sensors, right? We add more sensors. So if one fails, more sensors in the same area. If one sensor in the same area fails, we can use the rest of the sensors to generate the events we need, right? Okay, so we're done, right? We don't lose anything. Or can something go wrong?
If some sensors break in one area, the others in the same area are more likely to break. Right?
That's true, yeah. But that's very deep. I mean, okay, that's. But let's say we solve the issue of the sources. Basically, our sources are reliable, are highly available, right? But
I mean, Paris is just making a point. You have to make reliable sources here.
yeah,
What if your computer fails?
Yeah.
or the Flink when we run Flink. Well, yeah, if that fails, let's see what happens. So let's say the squirrel dies. And we actually thought about this, and we just recovered the system from scratch. Okay, that's fine, or is it not? So that means that we actually not process all these smoke events there between the time the squirrel dies and we restart it. That means that we will not detect a fire because the smoke is a very important event for fire detection, right? We need to actually put it in our pipeline. So what do we do here? There are resilient brokers. I mean, there are systems that actually do this job for us. So we can actually ask those systems, give me all the events I lost from this offset. So if we know the offset in the first place, we can actually ask a system like Kafka to give us a stream from a specific point in time. So it does what I say strongly consistent offset mapping to records. There's an offset map to every record, and that's consistent. We also have topic-based queues. Gila will talk more about it. I will not say more. Okay, and then we need the second thing that's very important. We need processing guarantees from the actual system because, okay, we actually reprocess the stream, but what happens to all the states we had before? I mean, we had the state machine there running. What was the state when the machine died? We need to know the state and recover it from that state. And different systems give you different guarantees. So Storm gives you, for example, at least once guarantees. That means that you might reprocess events, and that might lead to fault detections, for example. We don't want that. It does this through event dependency tracking. So it keeps basically a tree of all operators processed a specific event in the whole timeline. And if there's a timeout, it just resends this event. So it buffers all these events in the source. In case of Spark, we have source upstream backup. So when we create an RDD, it's a resilient data structure. So we actually replicate this RDD to many machines, and we continue from there. And if there's a worker failing, then what we actually do on Spark is that we do parallel recovery. So we recover all lost RDDs basically throughout the time the worker died. But in case of Flink, we do something more clever actually, in my opinion. And that's not because we made it. It's actually there's a nice blog post on the Data Artisan's website to check. So Flink, what actually Flink does is that it provides exactly once guarantees on a real streaming system. And it does this through periodic snapshots. And it's not as easy as it sounds, but what it does basically that it propagates a checkpoint request through all the operators, and it creates a consistent distributed snapshot of all states, basically, and then recovers from those states when failures happen. Okay, so let's stick to Flink, actually. I feel very safe with Flink. It's fast. But
So
also include...
What's the benefit of the approach, putting the periodic snapshots the way you described it over essentially the other ones? So because both Spark and Flink achieve exactly on semantics through that, right? So,
True.
So why do you need this mechanism? Why? If you say it's more clever, so why is it more beneficial? Just to understand.
First of all, we do the minimal work. We keep the minimal state we need for rerunning our job. So our algorithm is, so we could use something like channel import, which is an algorithm that persists everything in our execution graph, like buffer states. We could persist like all possible states in our graph, but we don't want to do that. What we can actually do is that we can, when we propagate barriers, we can actually superimpose checkpointing over the computation without affecting the actual computation. So the whole process happens asynchronously. We don't need to stop the computation and say buffer everything now, persist everything now. What we do is that we actually do something more elegant. We just throw within the data, we throw some barriers. These barriers doesn't slow up the computation. They just indicate where we need to actually do a consistent snapshot. So that's why I say we superimpose the checkpointing. And basically, we don't need to block unless we have multiple inputs, and we need to actually have to align the barriers on all our inputs.
So effectively, you would expect a performance improvement through that.
Yeah, and of course.
One can also say that we exploit the characteristics of the data flow graph in our checkpointing compared to a very general Shandy-Paxos
Lamport
algorithm, which is actually a two-round algorithm, where a one-round algorithm.
So it's one round, basically, yeah, and asynchronous, purely asynchronous. Yeah, I think that's all. And basically, when we have cyclic data flows, we can actually treat them separately. So it's a special case, and it's also the minimal state we can keep. So you can check this algorithm on archive. There's a first version.
But I want to understand the difference between Storm and Flink fault tolerances. Like suppose Storm goes for record by record, like it has this acknowledgement system.
Yeah.
And Flink goes like a snapshot or.
Yeah, the main difference is that on Storm, when you resend an event, you actually break the consistency because you don't have FIFO ordering, you don't have partial ordering anymore. So that means that you might process a smoke event when there's no smoke, actually, because you just happen to lose this event when there was an actual fire, like in the past, right?
But do you think the Storm's approach is better for time series analysis? Like you need to maintain the.
No way. No, for time series analysis, you need exactly once processing.
So the risk that you have with the approach of Storm is you might get erroneous results, essentially, right?
Yeah.
You'll get wrong results if you do a replay, essentially.
Exactly. You replay in the wrong time, basically. So you can do it.
A question about Storm for you, because do the programmer do have to write something specific to falter?
Yeah, basically, I think you can see this in the example I wrote. It's quite obvious. So when we emit something, we actually need to relate an input tuple to our output. So that gives the system a hook to a dependency, to create a dependency tree from source tuples to sync tuples, basically. So it creates the execution graph of it creates a lifetime of a tuple, basically. And they do this with a binary, very clever technique. They do XORs, and when the XOR, the result is 0, then
we don't need to do anything.
We don't need to do that, yeah.
Yeah, but without the message brokers, for example, Capco or anything else, will it have the same fault tolerance as Storm?
Which?
Without the message brokers like Kafka, will Flink also have the same?
Not really, because Kafka is very important, because if you restart your sources, you need to also process.
Use the timestamps.
That's another problem, yeah.
But,
So-
but Storm also suffers from this problem. It keeps a limited like buffer for the input record and it drops them.
So you mean Storm can work without Kafka? Or?
Yeah, I was like thinking about that.
I see.
Somewhere, right?
What?
You also need to store the checkpoints somewhere, right? That's why you
True.
use Zookeeper.
Yeah.
So you also have.
But we don't store checkpoint. We don't store anything in the Zookeeper. That's an overkill.
Where do you store your checkpoints?
We have right now we have two different backends in-memory application that happens in the job manager, and that's basically where we keep the state handles. Let's say.
So you store them in the job manager.
Yeah, for now. That's our prototype. Also, we support HDFS backend as well, so we can actually. Okay, we replicate the state handles in the job manager, but that's just references, right?
So another thing that I didn't quite understand, so in your checkpointing scheme, do you actually take a global checkpoint?
Yeah, it's a global
You
check.
always have to checkpoint everything.
So it's a-
Synchronously, but you always have to checkpoint
Exactly.
everything.
So it's basically you can think of it as an atomic commit of the whole execution graph.
Okay.
So either everything succeeds or fails. So we can only recover for a globally succeeded
Of the latest global.
checkpoint. Yeah.
But we can do selectively. Clever.
Yeah.
Implement it, but the algorithm is there.
Yeah.
But you can't checkpoint part of your state and instead decide to recompute other state. So you always need to decide to checkpoint everything.
Yeah. We let the user decide which state is important and what state is not. So we don't do this eagerly. It's more like something that explicitly is defined by the user. And there, Gyula, I think, will show.
The nice thing is that the
Checkpointing, right?
benchmarking, it's very low overhead. Of course, it will depend on how much state.
If
that
the
you
state
get.
Yeah.
is small.
Yeah, and maybe you can do some tricks to even to have incremental state updates. I mean, compared to the last.
Yeah. So that's something we are currently working on as well. And that's our whole pipeline. We have Kafka now. We have Flink, and we can go to bed safe and wake up. We don't die. That's very important.
Do you do you really made experience with the Arduino board and
I've played around, but I didn't make this example. I didn't implement it. But I like Arduino. I have mini one.
yeah.
And these are, by the way, if we have master students here, we have some cool research topics if you're interested to do your master thesis, for example.
So this is a call for doing master thesis.
Exactly. At 6 and KTH.
So I think
So these are the topics we are currently working on. There's also Vasya involved. He's not here today. So Vasya is mainly working on streaming graphs. And we also have topics like exactly once guarantees, state management. If you're into systems research, you can come to us. If you're into applications like machine learning pipelines, you can also do something there. We have some nice projects going on. Thanks a lot.